In this recording I will talk about one-factor models to model interest rates. As we already know, interest rates are quite important when it comes to bond price valuation, because these interest rates are our discount factors. Yeah, so whenever we try to model bond prices, we actually also have to model interest rates. Now, there is quite a substantial literature on these one- and multi-factor interest rate models, which goes back to the 1960s and 70s. And this area offers quite useful models that can be easily implemented for the purpose of valuation in various packages, including Python. So what I will basically do today is I will go through the process of translating, in fact, any model you would like to implement into something that can be simulated in Python. Now, first we have to note that these interest rate models, they tend to be so-called continuous time stochastic processes. Now, what does that mean? In these models, time is seen to be continuous. Yes, there is no discrete nature of time. Now, this has big implications from the theoretical perspective, because once time is continuous, I can use calculus. I can, derive a first derivative, and I can have a discussion about that. Yeah, of course, there might be some limitations in terms of how we should interpret these first derivatives and so on, depending on the type of process. But computationally, a continuous time framework is beneficial. It's easier for theory development. But if I want to implement that in any computational fashions, if I want to use a numeric method to simulate these processes, I always have to move into discrete time. So we have to take the step when we want to translate the mathematics of continuous time models into discrete time for the purpose of simulation. Now, I introduce here a little bit of notation, which is fairly standard across the literature. So usually R would denote the short rate, dr would be the change in the short rate, so this is a first difference in terms of notation. T is time, dt is the change in time, so this is a very marginal, tiny time interval. Of course, again, when we go into the simulation, this dt will be slightly bigger, because we have to have discrete steps. And then there's a random term, often denoted as z, or then dz is the change in the random process. We will come to this in a minute. So basically, these stochastic processes have certain features. So they tend to have a time component. You see this in the first part here. So there is a b delta t. So this is a time component. This component is deterministic. So if we ignore the dz, which is the stochastic component for the time being, the first part would be a standard differential equation, and I could actually derive it using standard methods. Yeah, I can actually solve this equation. If I have initial conditions, I can of course have a complete solution for it. Now, in modeling, we always consider there is a stochastic element to prices. Now, this is generally assumed to be a process of novel new information that comes to the market, which leads to a change of the fundamental value. So this is usually captured in this random noise. We also perceive this random noise to be indeed really random, so there is no degree of predictability. So lots of assumptions we associate with the D set are all based on our theoretical understanding of how prices should behave. So for instance, we would assume that past movements don't give us any hints about future movements, because actually if they did, it would indicate that the market isn't really efficient. Yeah, so if you can predict future movements based on the past, well, you should then do it and implement a proper investment strategy to exploit that. And of course, when you do this in equilibrium, this opportunity should vanish. Yeah, so this is the whole idea of arbitrage-free pricing. So there's a strong link between stochastic processes that we use to model interest rates and our understanding of arbitrage-free markets, of equilibrium conditions. So we argue in equilibrium it is reasonable to assume that this random process is what you might call IID distributed, so identically independently distributed. There's no correlation between past and present realizations of this random process. Now there are different terms you might come across. So B, so this is the term for the component which is driven by time, is usually referred to as a drift component. So basically if B is positive, you would see this process drifting into the positive direction. If it's negative, it will go into the negative direction. Then we tend to have a scaling parameter, often used as sigma. So if you think about this for a second, the first part is deterministic, yeah. So it doesn't have any variance. If you take the variance of the right-hand side, you would get sigma squared, because it's a parameter. It goes to the power of 2 in variance calculation, times the variance of whatever this D set is. Yeah? So this sigma squared basically is a measure of variance. Now it is a convention to use these scaling parameters. So that's entirely, of course, a convention. You could also move it into this random term D set, but we made the decision to keep it separate. So usually D set has a unit variance. You know, so we tend to standardize it. We tend to assume it is standard normal with zero mean and a unit variance. So that's a convention we adopt. Yeah, so that's very common across this literature. Of course, by doing what we are doing, we make a ton of assumptions, and just outline them here. And of course, as a consequence, and that's the interesting part, in the last part on that slide, we also then can derive the variance terms going forward. Yeah? So the idea here is the following. Because these random disturbances are IID distributed, that means they're independent. If you want to calculate the variance of a sum of these deviations, the variance is simply then derived as the number of times you have these random disturbances times the variance of each disturbance. Yeah? Or put differently, if I have capital T periods ahead, so we have capital T of these disturbances, the variance would be capital T. Yeah? And if I refer then to the standard deviation, I would simply take the square root of it. So that is simply a consequence of IID assumptions. Now, as I mentioned before, there is a strong link between the assumptions and our whole idea about asset pricing and equilibrium conditions. So to a large extent, I think this is rather acceptable. Of course, we can have a discussion whether normal distributions are the most plausible way of thinking about this. Empirically, there are certain doubts. However, there are of course, there is a huge amount of simplicity going on with normal distributions. I can do many things much easier, and in particular I know that just with 2 moments I can describe the distribution, which is not necessarily the case for other distributions. Now this is a general expression of what we just saw. So in general, this drift component and this scaling term, they tend to depend on time and also on the value of the interest rate. And we come to this in a minute. Now there are various modifications of this general formula, but this is basically the starting point for this whole literature on single factor models, where we focus on the interest rate as the driving force for its own progress. So basically it's a bit like in univariate statistics, where you model a time series using only the past realizations of that particular time series without going into how this is related to other time series. Otherwise you go into a multivariate approach, and this would then move you into a multi-factor model. Yeah, so here we are in a one-factor or single-factor model. Now what we observe as standard fact in the case of interest rates is the following. Interest rates tend to move back to a long-term equilibrium. At least this is true for most time periods. One has to be honest. The recent very low interest rate period is a bit of an outlier. Yeah, this is quite uncommon, but usually you would expect interest rates to go back to a long-term equilibrium. So it's not like looking at a share price. Share prices are quite well understood in terms of modeling as a random walk, and they might drift up or down without any bounds. Of course, meaningful lower bound is obviously 0. Which you can achieve depending on the way you want to model it. But in the case of interest rates, you would assume that they tend back to a long-term equilibrium condition. Now, there is a good debate, of course, on the volatility element of interest rates. To what extent are these elements predictable? And exactly how do we want to model it? And there is a debate in the literature, and there are different solutions to that problem. So in most cases, of course, you will make simplifying assumptions. Yeah? And one simple assumption is to assume that this variance term is maybe constant, the scale is constant, or it has a certain simplified pattern. Yeah? And of course, you will see there are different takes on how we should think about the volatility component. Now I want to talk about the Vasisek model. I'm sure I mispronounced that name, which I think was the first really successful but also quite influential model in this area, and it's heavily cited, which takes this form which we describe in this stochastic differential equation. So we would argue that the change in the interest rate is driven by a drift component which is mean reverting. Yeah, you see here the dependence on the level of R. So if B describes a long-term equilibrium of the price, which in this case is the interest rate, if you are below your long-term equilibrium, and assuming A is a positive factor, which is basically a measure of the speed of adjustment into equilibrium, then you would assume that this would track the rate up, and otherwise it would go down if you are overshooting your equilibrium. So that's the first component here. And then you have a stochastic component which depends here on dW, and dW is, we'll see this in a minute, a so-called Wiener process. So that we have to explore in terms of modeling in a bit more detail. But basically this model should give us a stochastic component, so you should get a degree of randomness in our interest rates, but we should also see a tendency for this model to go back into long-term equilibrium conditions. So what I want to do is I want to take that and I would like now to model this in Python. Because I think this is quite a good skill to have, to actually take this idea and move it out of theory into something I can actually model. And I want to talk you through this, how to do this. Once you see how this is done, you can easily take any other model, like the Cox-Ingersoll-Ross model, and try it there again, because it's a very, very similar model. It's very easy to modify. That would be maybe also a nice topic, for the group presentation. Yeah, just take this model and see how it behaves and what are the different factors. So now I move into Python. I opened my Spider. Let me just here clear my screen. I can also clear these variables. And I just might call this here interest rate models. Yeah, so I just start playing around a little bit. Now, what do we need basically? So let me just zoom this a little bit further. So what we need is definitely some degree of stochastic component. Yeah. I also would suggest, and I think that's always a good process, to really look into the original paper. So I have done this because very often, of course, the slides and usually the normal teaching material which one uses, they are all based on textbooks, which is, that's fine. But looking into the original paper can be quite interesting, because you will realize when you actually go through the paper that it's a much more general paper compared to the single equation which you see in most textbooks. And as a matter of fact, this is the more general form of this equation. And way back in the paper, this is I think the last part of the paper, this more specific form is discussed, and this is actually what most books would refer to. Let me just find it. I think here it is. Yeah, so this is a specific case. Yeah, and you see this is only an illustration of the general model. So it does not mean that this is the only way to model interest rates, but this is a general take on the model. And in fact, the paper refers here to an Ornstein-Uhlenbeck process. If you want to know more about these processes, you should definitely look that up. Very fascinating. Actually, I did a paper on these processes in the context of statistical physics. So they can be quite fascinating. So basically, these processes are mean reverting. Yes, they're mean reverting. You see this also in this equation. That's a mean reversion, assuming the parameter values are plausible. So you would have positive alpha, so this makes it mean reverting. Yeah, so that's the standard setting. The gamma would be something positive because we're talking about interest rates. And then you have here the rho, which is your scaling parameter. So that's the sigma. And dz is the so-called Wiener process. Now again, if you're not so sure about the different components, it is useful just to look them up. Now this is for the Wiener process. I'm quite sure most likely you have covered this in an asset pricing course, but you see certain properties. Yeah, so in particular the key property is actually summarized right here. So here we argue that if there is a time gap u between two realizations of this process, so basically this talks about the increments of the process, these increments are normally distributed with mean 0 and variance u. And this simply comes from the idea of having an IID distributed standard normal variable in between these two points, and if you add up these u independent error terms, of course you get a standard normal, you get a normal distribution with the variance of u, where u is basically the time gap. Yeah, so that's That's basically, you can interpret this from a discrete perspective as a process that is based on IID distributed standard normal random variables. Yeah? But of course it's a continuous process. Yeah? So mathematically it's a continuous process, but of course later when we now try to translate this into our numeric model, we will take this as a discrete process. Yeah? So that's quite helpful. So now we move into Python. So what do we need in Python? Now there are different ways to get random variables. Again, if you are unsure, it's always a good idea simply to have a little look at the different packages. For instance, in Python we have the random package, but also we have the NumPy package. So NumPy is very useful for numeric calculations and for so-called arrays. So when you look for NumPy random normal distribution, that's the one I would exploit, because the benefit of NumPy is I can generate these normal distributions not only for one particular value but for whole arrays. So that can be helpful in this setting. And now here we see the details about it and also how to implement this. You see down there, that's the implementation. So in terms of syntax, we note we have here basically the location, so that's the mean, we have the scale. So that is a measure either of standard deviation or variance. We have to check that. So we see it here, it's standard deviation actually. So it's important to note. So we have here the mean and the standard deviation, and then we have a size measure. The size measure basically would allow me to use that for various shapes. Yeah, so I can use it for various arrays. So that can be computationally very beneficial and quick. So it's interesting to note this. So it might be useful to do here an import statement, numpy as np, so that's always a good start. I usually want to plot stuff, so I also import matplotlib.pyplot, if I don't misspell, as plt, because we anyway want to do some plotting later. So now looking at our problem, so when we go back to the slide, we have here first to consider this Wiener process and with a scaling parameter. So we have to think about how we do that. And then we have to put this together into this equation. So I think it might make sense to do the Wiener process first. So, so what do we need? Let me just maybe write this down. Wiener process. Now let's think about this. So what are the elements we might need? We certainly might need n, which would be in our case the number of steps. So how many steps do I want to take? I just not take 1000. Yeah. So n is the number of steps or iterations in our model. So this is the number of times we want to model it. So this would be the length of our array in this case. Then what else do we need? We need of course time steps. Yeah, and here we note, because nothing is discrete once you do a numeric model, that the delta t, so this time gap, might not be 1. 1 is a bit too big. We do something smaller. We have to play around later with the numbers. Maybe a 0.05 might be okay. So these are the tiny time steps. Then we have the scale or the scaling parameter, which is denoted rho. Which you might put wherever you want to put it. I just put it at 1. Yeah. So that should be okay. Yeah. Let's just try and see what happens. Yeah. I'm not sure about the spelling of rho. Is that the Greek rho? Not entirely sure. Let's just check. Might not be the case. See, it's not. I thought so. Here we go. Always beautiful to have Google. Good, so now we have the scale, which is row. So we have the time steps, which is, that's fine. And now it would be useful to specify my target array. So that's kind of a good thing to do. You don't always have to do this, but it's kind of useful to know what you're aiming for. And what I might suggest here is to call this like the output vector, or just do it now W for Wiener process. So that's my array. Initially I don't have any values to start with, so I just use np zeros, which simply puts in all zeros. Yeah, and I just use the number of steps as the size of my array. So if I run this, what happens is I get now this array of size 1000 and all values are equal to 0. Good. Now what we need is we need now to construct that. So how would you construct it? Well, we need initial values, and then we have to go basically through a loop where we start adding up these different components. And then we have to be careful with our scale and also with the time step, yeah, because we know in the Wiener process that the variance scales with delta t. And so if I operate on my standard deviation, it would be the square root of dt. So that's basically what it is. So let me just start with an initial value, and let me just we can either really specify a value, we can do that, or we can already here now consider doing a random draw. We could do that. Let's do the random draw. So we do an np, and I think it's random. And I think now we have to go back to what we found here. It's random.normal, and we have the structure. Okay, let's do that. So it's random.normal. Let's do that. And put in 0 and 1. And of course, in our model, we scale up by our factor row. So that's fine. We scale that up. And then we should also consider our step here. So I would do np sqrt, so that's square root, and where we put in dt as our step. Let me just make some space in between to make it a bit more readable. So that would be our first random variable, and then we would start cumulating. Yeah. So basically, adding this up, so yeah, adding terms. Yeah, so how can we do this? Well, we can do this in a for loop. So for idx is the index in range, and we have starting at 1 going up to n, and we write this now as follows. We do maybe we use here j, that's enough. Let's do that. And what I do is I go to the previous value of j, which is j minus 1. And of course, if I start at 1, this would bring me to my initial value. This is why I have to specify initial values, otherwise I would run here into a problem if it's not specified. So I take the previous value, and then I have an innovation, a new value. And the new value is, well, it's just what I have here, basically. Yeah, I just do this draw out of my standard normal distribution, and that's basically what it is. That should do it, and then we should be able to plot the function. So plt plot w. This is not necessarily the best way of doing it. I just mentioned it. There are better ways, faster ways of doing this using vectorization, but for us this is a little bit more intuitive, hopefully. Good, let me just run this and see how far we get. Okay, so now we have here the output, that's pretty good. So that looks Looks just like yeah, a Wiener process. It's not bad. We run this one more time. Here we go. Yeah, looks all decent. Good. Now what we of course notice whenever we run this, we get a new realization of this process. Now for testing, it's better you fix it. So it's useful, in fact, here to define the so-called random seed. Yeah, so that's a useful process. So in NumPy, we have to check how to find this. So NumPy random seed, we just have a little look how we do this, and that's the syntax. So we just take that. So we fix the random seed. So that will fix the realization. We used MP for NumPy, so we abbreviate that. We specify here seed, and we just take any number we want. We just take number 1, for instance, and run this one more time. And now whenever you run it, it should be the same outcome. You see that? So that's good, because that makes it for us easier than to realize whether we make any mistakes. Good, so now we have specified our Wiener process. Now there is a disadvantage, because this is of course now not specified as a function, so we can't refer to this later. And actually I would like to refer to this later, because well, I use the Wiener process later. So I mark everything, I do a tab, so I do an indentation, and I define a function which I call Wiener. And I specify some arguments. Now what are the arguments? Well, anything I specified here. Yeah, so we need definitely n, we need our time step, we need our scale. So all of that we need. Nothing else is needed, so that should be fine. The plotting honestly doesn't need to be in the function. Yeah, we can just throw this below. We might just maybe comment this out for the time being. So that's Wiener process. It would be useful here to do a docstring and simply generate a default and just specify what we use. This should return, of course, something. It should return an array, yeah, of dimension n, yeah, containing our Wiener process. Yeah, so this is basically my output, if I can spell properly. Here we go. Yeah, so that is of course the number of steps. We have specified that. So number of steps, which should be an integer. We can also now of course say here this should be an integer. This of course can be ignored basically. We don't have to. So usually I don't specify it. I tend to not specify it, because anyway Python will ignore it. And this is here my time steps. So my time step, actually it doesn't have to be a plural. And this is my scale. So that's the scale. And here we are. So we don't need any of that, because we have already specified that. We take the target array and then we run it. That should do it. And now I have to do a return value. So if I only run this, nothing happens and nothing is returned. So I have to specify here return, and I just call this w. And then I could simply test it. I just test it now. And I just call this w is equal to my Wiener function. And now I throw in various values. For instance, let's put in here 1000. We have a time step of 0.05. And we have a row of, say, 1. And then I want to plot this. Okay, let me just see. Let's run it one more time. So this is basically what I have done is you call this refactoring. So I changed the code, moved it into a function. I run it one more time and it's working as expected, which is pretty cool. Okay, good. So now we again comment this out. We don't really need these steps in between. The next thing is now I want to have my actual model. Yeah, so if I go back, this is actually what I want to have. So I have a few more parameters. I have an alpha, I have, I think in the paper it's called gamma, and so on, and all the other components. So how do I do that? Okay, that's interesting. Let me just try to figure this out. So again, it might be useful to throw this into a function. So that's now my model. I just call this model. Yeah, so I call this model. I need a few more parameters here because I need an alpha and I need the gamma as well. Do I need anything else? Let me just quickly check the paper. So we need alpha, we need the gamma, and the rest should be okay. I don't think there is much else. Yeah, might have forgotten something. We will figure it out. And again, I do here my doc string. I do generate this, and we just partly copy paste that. So we just have all the same processes, except that in the end we get a different output. Yeah, yeah. Let me just put that here. Yeah. So we have our numbers as expected. We have the alpha, we have the gamma. So let me just copy paste that down. So number of steps, the time step, the scale, and the alpha is actually like a speed of adjustment. Yeah, so this basically tells me how quickly you go back into equilibrium. The gamma is like a long-term equilibrium. And then I get an array of dimension n containing basically the interest rate process. Yeah. Okay. So that's quite good. So that is our starting point. Now let's model this out. And as a matter of fact, I think it could look quite similar. We could also do a target. We can just anyway copy paste that and modify this basically. So we can have also here a target. You might like to take a different name, but honestly speaking you don't have to, because you're inside the function, so the scope for this local variable is restricted to the function, so it doesn't matter. We might need an initial value. This is not that obvious what it should be, so usually you might actually like to specify something like an initial price value. I just call this P0. Maybe let me also move it into P for price. Let's change that into price. And so P0 would be the observed interest rate, for instance. Yeah, so P0 would be the initial interest rate. So the current interest rate, for instance, you can use that. Then we have again here this range. Now we have to modify this, and basically if you remember, let's just move into this step by step. So what I do is I literally take our equation and move it in. So what I have here in a continuous time framework, I basically have the change of price on my left hand side. So this is exactly this part of the equation. Then I have alpha in brackets the gamma minus the actual price times time, and then I have the random process, the Wiener process. The Wiener process already has the row, the scale, so basically here inside this function I just have to call the Wiener function. Yeah, so basically I just use this function here inside. So this is covering my stochastic process, and now I have here only the alpha to take care of, alpha, and then in brackets this is plus. I multiply this, I should be careful here, and then I get the gamma, and I have it minus the price level in the previous period. Yeah, and you will see this in a minute. Times time, and time is delta t. Yeah, so that should do it. Now, of course, this wouldn't work. Yeah, it doesn't understand, of course, equations. So I have to move this here to the other side using a plus, basically. Yeah. So basically, the interest rate is equal to the old interest rate plus the change in the interest rate, yeah, which is driven by alpha times the gamma minus the previous interest rate value times delta. Of course, I can only talk about the past here on the right hand side because I don't know the future. So if my current value, which is j minus 1, is below the gamma, which means you are below the long-term equilibrium condition, alpha should be positive, then you would expect a drift up in your interest rate. And then you have the Wiener process. Well, let's test that. We return here, of course, p. Otherwise it will complain. Let me just tidy this up a bit. Yeah, we don't need the additional space here. Okay, it's all tidied up. Good, and we just now try it. So basically what I do now is I just take this, copy paste that below, and here I now try to initialize my price process. I take these values, and now we have to just play around with the values and see what happens, and I plot here price. Let's do that. I have to, of course, specify now, so let's put in here, say 10,000. We have 0.5, we take rho to be equal to 1, we can later play around. Maybe we have to reduce it already a bit, we have to play around a bit. Alpha is anything positive, we just maybe start with 5, we have to see. Yeah, so let's do that. I tidy this up a little bit. So we can do this, tidy up, so we have it all in one row. The gamma is our equilibrium value, say it's 6%, yeah, and our initial level might be below that. I now speculate. And let's just try that and simulate that, and of course I might have made a few mistakes on the way. Let's run this. Okay, setting an array element with a sequence. Oh yes, of course, that's true. Because now what I have done here is I put in an array. Yeah, because the Wiener function is an array. So that's not a clever idea. We have to do this in another step. Yeah, so this is here our Wiener process. So what I need is I have to put this into a W, that's the Wiener process, and just write this. Yeah, so this basically gives me an array which is W, which contains the realization of the Wiener process, and then I threw in this array in here, but I start indexing this with J. Okay, so that should do it. Good. If you have any questions on that, let me know in our live session. I'm happy to discuss that further. So let me just run this through, and you see this looks a bit extreme. That's a bit extreme. Okay, so let me now just play around with the figures. So something is working for sure, but maybe the figures are not quite realistic. Okay, let me just, yeah, I think we have a very high value for time, so 0.05. Let's run this one more time. That looks more plausible, much more plausible, but you see quite strong deviations from the equilibrium. We are far away from the equilibrium, so we can now play around. So we can reduce the rho, which is our scaling parameter, so we can make it much smaller. So basically reduce the stochastic element, and then you see actually what is happening in the model. You see that if you almost diminish totally the stochastic element, you see you jump from your initial value right into equilibrium. You see that. And then you stay in equilibrium. So that's of course very extreme. But you see it's very nice to have these models implemented in Python, because now you can start, playing around and try to understand what happens if things change. So if I now increase the disturbance, you will see that slowly becomes more realistic. Yeah. So again, you have this initial jump, and then it seems to be more realistic in this setting. Maybe also the alpha is quite strong, because this is forcing us quite quickly back into equilibrium. We might have a much lower value here, it's maybe a 0.9 value. Yeah, and we have to play around. Now this seems to be a bit more realistic, and you see more drifting off in this case. Yeah, so here you can start playing around with this model. But the main thing I want to convey is you can move from a continuous time model to a simulation in Python, where you translate this into discrete time and you implement it accordingly. The benefit of doing that is I can now run it, of course, as a Python asset pricing model. So of course, once I simulate my interest rates, I can simulate not, of course, only one time series, but a few thousand time series. And then I can, of course, derive expectations over it, and then I can derive expected, prices for bonds and all sorts of other assets I would like to price. Good, that's all for this session. I hope you enjoyed. I see you in the next.